centroid is the center of a mass of an object if you assume that the object has uniform mass, uniform density. So let's think about an example that we actually know. If you have a triangle, how do you get the center of mass, or the centroid?
Directly down the middle.
Yeah?
You bisect each of the sides.
Yeah, you bisect each of the sides, and then they all meet, right? They all meet at a single point, and that's called the center of mass of a triangle. And in fact, if you imagine that this triangle is drawn on cardboard and you cut it out so that it has some weight, if you put your finger right at this point, then you can balance the triangle. Whereas if you put your finger at any other places, it's going to tilt and fall down. So that's the centroid. Now, as engineers, you guys would be interested in knowing the center of mass of an object because when you describe Newtonian motion, when you do engineering mechanics or statics, Newton's great idea was that even though things have shapes and sometimes it could be really complicated, you can still describe the motion of a moving particle as if it's a point particle at the center of mass. So when you have something like this thrown in space, then you can just think of it as a point particle at its center of mass. That's why it's important for describing the motions of objects. Now, the second thing I want to talk about is the fact that center of mass is really the average, or actually weighted average of coordinates. And to explain what I mean by this, imagine that you're on a seesaw. So you've been on a seesaw when you're little, right? When you were a little kid, right? With your dad. So let's say back then your dad was pretty big and small. Then in order to be balanced, the center of mass should be somewhere here, closer to your dad. Right? You can even make this more accurate by putting some numbers here. So let's say your dad is 200 pounds, a little heavy, but just for the simplicity, okay? And when you were a little kid, you weighed 100 pounds, okay? And then let's say this length is 6 feet. And you want to know exactly which place should be the center of mass, ignoring the mass of the rod. Okay. Actually, if this is heavy, that's going to also play a big role. But let's say this rod is very thin and it's really just these two. In that case, if you say the kid is at the x coordinate equals x equals 1, and your dad is at 1 plus 6, which is at 7, and you wanted to know the coordinate of the center of mass, you do like this. You do 100 times 1 plus 200 times 7 divided by 100 plus 200. So rather than just taking a simple mean value of 1 and 7 divided by 2, you give more weight to the dad's position because a heavier object is there, right? Okay. And then you divide by the total weight,
X equals to 5.
and then you'll end up with 5, yes. No, yeah, 5, it will be 5, okay. Good, it's fast. Right. So that's where the center of mass will be. Now we're going to tie all this together by solving a question that does come into play when you do engineering statics, which is, let's say you have a circle of radius A, and you want to find the center of mass here. And I know because of symmetry, if you have a, oh, by the way, we're thinking of half circle, okay? So let's say we have a half circle centered at the origin of radius A. And you want to find the center of mass of this object, okay? And we assume that this object has uniform density. That's why it's called centroid. So we want to find a centroid of a half circle. That's the question. Now for this, we know that the x coordinate should be 0. But this y coordinate, we don't know what that would be. Some value. We can make some guesses, which is like, if you compare it with the triangle, then you have more stuff on the top than a triangle. And we know that triangle is like a third of the height. So if you have an isosceles triangle, and if you do this midpoint thing that we just discussed, then you also learned in high school geometry that the ratio between this to this is 2 to 1. Do you remember that? 1 to 2? That's something you learned in high school geometry. So that means since it's 1 to 2, that means this height would be a third of the entire height. This would be 1/3 of the height. And because a circle has more stuff on the top, this value will be bigger than 1/3 of A. On the other hand, we know that this y coordinate of the center of mass must be less than 1/2, because if you have a rectangle, the center of mass will be exactly 1/2, right? But there's more stuff in the bottom than the top, so the center of mass should be less than 1/2, but bigger than 1/3. There's some value between them. Okay. But that's not the point. We actually want to find the formula for it exactly by using integration. So how do we do that? Well, first we have to come up with this value mu, which is the surface density. Okay, do you remember what the definition of surface density was? Mass divided by?
Volume.
No, the regular density is mass divided by volume, but surface density is a two-dimensional thing.
Mass divided by area.
Area, so you divide by area. And then we also had the linear density where you had the mass divided by length, right? So you have different types of density, where the usual density is the mass divided by volume. But see, we're working with a two-dimensional object, so our density will be mass divided by area. And then we want to find the average value of the y coordinates of all these points. So the idea is like, imagine that every point on this half circle has some weight, and you just calculate the average value of their y coordinates, and that will be the value of y bar. That's how we're going to do it. Yes?
Does y bar just basically mean -y?
No, no, no. So when you say some function bar, that means the average. This bar means average value. Okay? That's a notation people use. So when you put a bar on top, that means it's the average value of the quantity. So we're really trying to find all the average values of every point on this circle. So what we want to do is we want to take this and divide it into very, very thin pieces. And the reason we want to divide it into horizontal pieces is because for these points on the same piece, they have the same y value, right? So a single strip that you choose will have the same y value as its y coordinate. And as we said, y bar is a weighted average, which means first you multiply y by the weight of this strip. And weight of the strip is mu times dA, because this really means that if you multiply by area, you get mu times A equals to mass. So if you take the surface density and multiply by the area, you get the mass. Therefore, multiplying the surface density by the area of this fine strip will give you the small mass assigned to that strip. Okay. So this much really is dm. Okay. So that's your weight. The value times weight is added, just like how we do it, right? The value and the weight is multiplied, and then you divide it by the total weight. Okay? That's how you do weighted average. So you divide it by the total weight, which is again this. Now we can pull the mu outside because we are assuming uniform density. So that uniform density means that mu is constant. Any constant can be brought outside the integral. So these can cancel. And we can even figure out what integral of dA is. Now if you add up all the small areas, what would you get? If you add up all the small areas, what would you get? Sum of small areas will become?
Sum of dA.
No, what would you get if you integrate this? Integral, you add up all the small bits of area as you move from here to there. Right? What would you get? This plus this plus this plus these infinitely small pieces added up, what would you get? The area. You'll get the area of the entire thing, right? And we also know the area of this thing. What's the area of this? As the area. What's the area of the circle? Pi r squared, but it's a half circle, so it must be 1/2 pi a squared, because we're assuming the radius is a. Okay, so we also know that this is 1/2 pi a squared. That means we just have to focus on how to find the top. Now let's try to figure out how to find this area. Well, what's the thickness? Thickness is?
dy.
dy. It's a thickness in the y direction, dy. And how do you get the length? How do you get this length?
dx.
No?
The equation.
You use the equation, but what was like the formula you always use when you want to get the length? What was it?
Pi times r. What's the one?
No.
Base times weight.
That's what we're going to do to find the area. dA is L times dy, base times height, right? But I need to find the value of L, or L as a function of y. How do you get that?
dA over dy.
Come on, we did this several times.
That is so ridiculous.
I mean, the idea that we always use is either you split into horizontal strips or vertical strips. If you have horizontal strips, what do you use?
Yeah.
It's right minus left, okay? For horizontal strips, how do you get the length? Right minus left. For vertical strips, how do you get the length?
Top minus bottom.
Top minus bottom. I thought we went over this several times last time. So please don't forget, okay? Anytime you want this length, we do right minus left. If it's a vertical one, we do top minus bottom. Okay? So that means we need to know this portion minus that portion, because this strip is from here to there, right? So you have to do right minus left. So we need to find the formula for this arc and formula for this arc so that we can subtract. And more importantly, because we have dy, these functions better be functions of y. If it's functions of x, it doesn't work. Okay? You have to make it as functions of y anytime you pick dy. Right? Okay, so let's go back to this equation of the circle. This circle equation, as you know, it's x squared plus y squared equals to r squared, but our radius is a, so this is what you have, right? So start with that equation, x squared plus y squared equal to a squared. But you want the function of y. So should I solve for x or should I solve for y?
Solve for y.
If you solve for y, you get y as a function of x.
Solve for x.
You have to solve for x because you want a function of y. Yeah. So x squared is a squared minus y squared, and you solve for x, you get x equals to plus minus square root of a squared minus y squared. And you first notice that there's a plus and a minus, but that's expected because if you just have x equals to plus square root of a squared minus y squared, that's going to give you the right half of the circle. Whereas x equals to negative square root of a squared minus y squared, it's going to give you the left half of the circle. That's because square roots only give you positive. So if you have this equation, you're only going to get a portion of the circle where x coordinate is positive. And if you do this, you're only going to get the portion of the circle where x coordinate is negative. So now it's clear what right minus left is. Your L would be, the right would be this one, minus the left, which is negative square root of a squared minus y squared, which will become twice of square root of a squared minus y squared. Okay, now that we know what dA is, we can now calculate integral of y dA, which is integral of y times dA. We found out to be L times dy, but L is this, so 2 times square root of a squared minus y squared times dy. And because it's a half circle, y doesn't go from negative a to a, but it just goes from 0 to a, right? 0 to a.
So that's how we basically cut the bottom off.
Yeah, so some of you might have been puzzled why I had a half circle like this, but now I have the bottom ones. Well, this one gives you actually the full circle, but if you limit this circle with y being 0 to a, you will get only the top half circle. So if you take these graphs and you limit your y to be between 0 to a, then it's going to delete the bottom halves and you only get these two. Okay? Now let's try to calculate this integral, which is, no, this is getting too complicated, so let me erase this part. And I'll just copy this over here again. So you can bring this 1/2 as on the top, L's right in front, so you know that y bar would be 2 over pi a squared integral of y dA. And we just found out that this integral would be 0 to a of y times 2 times square root of a squared minus y squared dy. Okay, now let's carry on the calculation. We're going to do u substitution as the entire square root, so that if you square both sides, you get u squared equals to a squared minus y squared. If you differentiate both sides, u squared differentiates to 2u. This differentiates to 2y, but as you know, you have to attach du if you're differentiating a function of u, and you have to attach dy if you're differentiating a function of y. Solve for dy by dividing this to the other side, so that dy is equal to 2u over negative 2y du. 2 cancels, so you get u over negative y. Moreover, since this is a definite integral, you also have to change the endpoints, right? So when y is 0, u is square root of a squared minus 0, which is square root of a squared. That's just a. When y is a, then u is equal to square root of a squared minus a squared, which is just 0, which is 0. So now that allows us to rewrite the integral in the following way. When y is 0, when y is 0, u is a. When y is a, u is 0. Y times 2 times, we decide to call the entire square root as u. And we also know that dy is equal to u over negative y, du. So that y can cancel. And furthermore, we can use this negative to flip these two around. The reason I want to do that is because usually you want the bottom number to be lower than the top, right? So it's more natural to have 0 to a rather than a to 0. So we flip this around, and that gives you 2 over pi a squared. Integral from 0 to a. Integral from 0 to a. Negative is now gone. It was used to switch these two around. And you have 2u squared after canceling. And that integration is 2 over pi a squared. U squared integrates to 2 over 3 u cubed. You plug in a and 0, so that this becomes 2 times 2 is 4, 3 times pi is 3 pi. And then when a is plugged in, you get a cubed divided by a squared, which is just a. So that is what you get. And to kind of get the idea of where this location is, pi is about 3, right? So here's what it means from the picture. 4 over 3 pi is about 4 over 9. And 4 over 9 is indeed less than 1/2, as we expected. And 4 over 9 is bigger than 3 over 9, which is equals to 1/3. So this value is indeed between 1/3 and 1/2. It's bigger than 1/3, less than 1/2. And that's exactly the point. This is 4 over 3 pi. A is the location slightly below the half, which is the center of mass of this half circle. Yes?
How did you go from the integral to 4 over 3 pi a?
Right, so maybe I went too fast on here. What really happened was this is 2 over pi a squared times 2 over 3 a cubed. After plugging this, right? A goes into u. When you plug in 0, you don't get anything, so this is what you have. And then a cubed divided by a squared gives you a. 2 times 2 is 4, and you have 3 pi. Yes?
When you took the integration over there,
Mhm.
where did the a square go?
A squared, see, when you have u equals the square root of a squared minus y squared, and when you differentiate this, a is a constant, it doesn't change.
So you just pulled it out, right?
So, no, when you differentiate a constant, what do you get? It's zero. That's why it doesn't
Yeah.
show up.
Okay.
It only shows up here after doing the change of variables. Any other questions?